Yes, we
Good
can. Good
morning.
morning.
Excellent. So it's about the time to start. So we'll continue from where we were left last time. We spoke about screw joints, different characteristics on them, and I think this is the slide we were left. We were just about to go to screw manufacturing. Previously, we handled the fatigue strength of the screw, and we learned the factors that would affect on the fatigue on the screw joint. Um, Most common methods of screw manufacturing are turning, meaning machining, and cold or hot forming or rolling for the thread and the shank, and forging for the bolt head. So more or less uh, plasticization forming for the billet of the bolt. Um, Modern methods have made it possible to manufacture bolts also with other means. For example, 3D printing if you require special characteristics inside the bolt, but that is not that commonly used. So if you go to the shop and buy a screw from Wurt or some other major dealer of screw materials, usually they are manufactured with forming and forging, because that is by far the quickest method of creating the thread geometry onto the bolt shank. But turned or machined screws are also used. The benefit of the turned screw is that it is a bit more precise. So by turning, you can find turned screws. You can find, for example, in machining machinery where you need quite precise thread and also micrometers and etc. But basically, pretty much most of the fastening screws, they are manufactured with forming and forging. And what is important to know is that this manufacturing method on the thread, it has a huge impact on the fatigue strength of the screw. So in this, it goes in a way that the ones that are manufactured with the forming, they have better fatigue strength than the ones that have been turned. And the reason is that by forming, it's possible to, by forming, it's creating a smoothening area on the thread bottom. There's also strain hardening of the surface of the material because it's basically plasticizing or forming the material. So there is strain hardening happening, and also by forming, it's introducing a compressive residual stress in the surface of the bolt all over. And a compressive residual stress is always beneficial when it comes to fatigue. So if you have a compression already in the surface of the material, it is helping us with the fatigue lifetime. So it's good to remember that residual stresses, they are not always a bad thing. Usually they are referred as being not a good thing overall, because they cause deformations, and if they are tensile, they cause higher stresses that are calculated from the loads. But if the residual stress is compressive, it will basically mean that it will reduce the effect of the load stress on the surface, and therefore it will reduce the stress effect on the surface to initiate the crack. And that is the linkage why compressive stress is good regarding fatigue. Okay, then we learned last time that tightness of the bolt joint in the preload and also preventing the loosening of the joint is quite important for the whole action or whole function of the screw joint. And therefore there are developed numerous ways of securing the bolt joint. Most simple ones are just putting some geometrical metal object which is preventing the nut from loosening or the screw from loosening. For example, a metal wire could be. In some motorcycles you find this kind of crown nuts where there's a little groove in the head of the nut and there's a hole in the screw, and you have to of course tighten this nut so that this slot would fit to the hole of the screw, and then you can put a wire through it. Another thing is that usually this can be used if you have specific thickness you need to tighten into. If there's a large play in the axial direction where you need to tighten the knot, then you would need, of course, multiple holes in the screw, and that wouldn't be good for the strength of the bolt. And by the way, I'm also speaking every now and then about screw and about the bolt. Have you ever heard or do you know what could be the difference between a bolt and a screw? Or is there a difference?
Maybe screw. Yeah, I think screw works like by its own, so that doesn't need any nuts, and bolts always goes with a nut.
Mm-hmm. It could be used that maybe somewhere. It's the bolt word is primarily used in the US. It's sometimes used also in Europe, and especially in Finnish, you have also two words. You have ruuvi, which is meaning the screw, and you have pultti, which is the bolt. But in Finnish, pultti is just a spoken language. It is not in any modern standards. It has been used in some very old standards, but nowadays they only use this Finnish word for screw. But in English literature you can find this bolt as well, and it a bit depends. It's not that straightforward. They are being used a bit mixed. So it's but some standards from America, for example, they tend to state that a screw that has a partial thread like this would be a bolt. And if you have full thread, then it would be a screw. That's one possibility. Or in some instances, they state, as you mentioned, that if there is a nut introduced, so that would be a bolt joint. But if there is just a screw and a tap hole, like well, I don't have a picture here, but if you have a tap hole in the counterpart, the component, then it would be a screw. But it's not that specific. So you can find these both words used mixed. Well, there's hardly ever any risk if you if you mix these two words. But just to know that they are not being defined quite well.
So practically there is no difference between screws and bolts.
Yes, you could say so. In some special fields in America, if they are accustomed to using bolt for specific partial thread screw, then they might say to you, but bolt is this one. But generally, nobody really can go really badly wrong if you use the bolt or screw. So you can use either. I've tried to use screw in my presentations because that is mainly used in the Europe, mainly. Okay, then there are some other means of geometrical locking of the screw joint, like locking plate. So there's a plate that can be bent to make an angle against the flat surface of the nut and then secured by a smaller screw or maybe against another component. Then one might then ask that how do you secure this screw over here? Well, Good question. But these are being used in some applications. So on top of each other, usually the locking nut or it could be of lesser thickness, depends. Then more used components are spring washers. So spring washers you can find in quite numerous places, for example in lawn movers and this kind of small equipment that shake heavily, that have high vibration. Spring washer are often being used, and sometimes these kind of serrated washers as well. And the idea is that they will prevent the loosening due to the fall of the outside or inside. And one option is so-called nylock nut, a lock nut which is introduced with a plastic ring inside this plastic. It cannot take high temperatures. It's usually maximum up to 120. There are some are up to 100.
Please repeat what you said in the past 15 seconds because I lost your sound.
Okay, good that you said. I didn't know anything. And top would be to use a lock nut, meaning nylock nuts, and it's just a nut introduced with a plastic ring inside the nut there. But of course, because it's plastic, it cannot change. So only up to 120 degrees of Celsius, some components up to 170. And the major draw in this stick tends to wear. So if you open it multiple times, then it doesn't basically function anymore. And anybody who's been dealing with this kind of bolts knows what is the concerning usability. What is the main drawback with these nuts? Have you been using these kind of in your practical work on or in your hobby projects or somewhere else? Why these are not so good to use? It's not easy to use. One, have you ever used this kind of or opened or tightened this kind of nut in any application? Everybody seems to be sleeping still. So do you think the ones, somebody put something in? Okay, so you try to tighten this nut with your hand. If you have a long distance to sort of to tighten the clearance away with your hand, it's quite not especially when it's to be so tight that you need a tool to tighten it all the way, even though it wouldn't be against the joining parts. If that isn't against the joining parts, you still need a tool because it's so tight from here. Drawback. So if you need to open them many times and you have a long distance that you need to sort of tighten the clearance away, it's quite time consuming and sometimes painful to do. But otherwise, they're okay if you don't need to open them too many times. Then there are thread forming screws. So basically a screw that has slightly, I would say, slightly bad thread. Maxim is asking, you have been using it? Yes. I would say it's usually plastic, but of course I've never seen one with a rubber ring. But of course there could be such also. Usually plastic, a nylon plastic ring over there. But of course could be rubber rings. Thread forming screw also. The good side is that it's usually quite secure because the bolt is or the screw is forming the adjacent tap thread against. It's usually quite secure to place it. What would with that or not good this.
Probably you cannot disassemble it for multiple times.
Exactly. And eventually, if you do that many times, it will destroy the thread. Okay, if you have a nut against it, you can always replace the nut. But especially in the application like here, so you would have a tap hole with the inside thread. If you destroy the inside thread, then it's gone. So only for applications where you wouldn't really need to open it. Then there's special washers called Nordlock washers, which are manufactured in a way that there are two washer plates against, and there's an angular shape between these washer plate surfaces. And the shape is formed in a way that this angle alpha, which is between the tapered surfaces of the plates, it's larger than the pitch of the thread, pitch angle of the thread. So therefore, if this bolt would like to turn open, it will basically face against the Nordlock washer taper angle and would prevent it from loosening. These are quite extensively being used in highly dynamic applications. But also if it's really heavy vibration, these also could get loose. Then one option which is also quite often used is to use the thread locking glue, like Loctite 243, like in the picture. This is medium strength glue, and Loctite 270 is the green one, which is the high strength. And if you use that one, you can't normally open the joint anymore just by using force. You usually need to apply heat also. So using 270 Loctite is so strong glue that you will first break the bolt, and the glue doesn't yield. But that's quite secure method if you apply it correctly and the surfaces are smooth. And the downside is of course also in this, that if you open it and you want to retighten the joint, it is possible, but you would first need to remove the Loctite residue from the bolt and from the thread. And if the thread is a inside thread, like here inside the component, sometimes it could be quite difficult to fully remove the glue from the thread surface. And if we look at this screw joint from a mechanical point of view, we can imagine the screw joint is like two nested springs. So two springs, of which another one is set inside to the other. And the bigger spring here in the picture, this light green bigger screw, that is the components that we want to compress. So there would be, of course, two components, a division line somewhere over here. But we can consider that these two plates would be this green spring over here. And then we have introduced a compression through a bolt or screw, which is now this black, smaller diameter spring inside it. And now this black spring is being drawn. It's under tensile load. And when these ends are connected, this tension in the screw in this black spring will want to press this green spring together, and all these springs are these components together. So it's compressing the green spring. Like in this lower picture, if we have a bolt, we have a green spring, which is the components, it's being compressed together, and we have a black spring, which is then under tension, and it's compressing the green spring. So they have equal length, equal force in the both, but not equal change in length. Usually these plates which we compress, they are by far with a bigger stiffness. So they are far more stiff than the bolt. So therefore the compression in millimeters in these joint parts in this green spring is smaller than the one that we have in this bolt in tension. And now when we think what is the balance drawing, how we could picturize this balance between these, so that we know that there is equal force but not equal change in length in these components. We can draw a diagram like this. So considering we have a relatively stiff screw and flexible joint members. So stiff screw would mean quite stiff black spring, and flexible joint members would mean that this green spring is fairly soft. And we can draw for both of these springs, we can draw a force displacement line. You understand that when we load the spring, the higher the force, the higher the displacement. So let us now draw a line for this screw, a force displacement line. So that would be now quite steep because we have a fairly stiff screw. It means that even though we increase the force, the displacement doesn't increase that rapidly because it's fairly stiff. And now when we remember that we have the same force acting in the bolt and in the joint members, we can start drawing the displacement curve from this bolt displacement curve. And from the point that we know where is the preload force. So when we tighten this screw joint, there's also, of course, a preload force. No other loads yet, no external load yet, just a preload force. And that force is, of course, equal in both of these. So now we define the preload force and we start drawing this force displacement line for the joint members. And now that would be in other direction comparing to the force displacement line of the screw, because that is in compression. And now we can, from this x-axis, we can read what is the displacement of the screw and what is the compression, so meaning negative displacement of the joint members with certain preloading force. So both of these start from 0 and they meet at the preload force, and then we can read what is the displacement for each of these. But now what is interesting is that Now when we introduce external load this system, we can draw the external load as a arrow into this preload force point. Because when we don't have the load, we just have this preload acting on this system. But when we introduce the external load, that will start to act from the preload for position. And by then we draw it in a way that if we know certain length of the external load vector, so certain magnitude of the external load, we draw it in a way that it will fit itself between these lines, between the force displacement line of the screw and the force displacement line of the joint members. And when we do this, we can then read how much of the external load is transferred to the screw and how much of the external load is transferred to the joint parts. And in this, it would mean that if we have this magnitude of external load, we have larger portion of the load coming to the screw. So that is added load to the screw in addition to the preload force. And a fairly small portion of the external load that is sort of going to the decompression of the joint parts. So this part which is going to the joint members means that this is the portion of the external load that is causing the decompression of the joint members.
Sorry, I have one question.
Yes, please.
Can you explain more clearly why in the joint member that the displacement will be bigger when the force is smaller? Or is it negative? So it would be opposite.
Yes, they are of course opposite. So in the joint members we have compression. So it's negative displacement. And then in the screw it's positive because it's in tension. So it's in other direction. And the reason that we have a smaller portion of the load to the joint parts in this setup, the reason is that this bolt is now so stiff and the joint members are so to say soft. So the stiffness of the screw is higher than the joint members. And that will cause us a situation where the major part of the external load is going to the screw. And that is not a good thing. You might understand it a bit easier in the next case if we compare into this situation, which is the better one. So in here you can see that now our screw force line for displacement is not that steep. So in here we had a fairly steep force displacement line for the screw, but in here the screw is flexible, which means that this force displacement line for the screw it's in lower angle. So increasing the force for the screw will increase more the displacement of the screw comparing to the case number 1 previously. And now if we introduce a force displacement line for the compressed members into this, and considering that we have very stiff joint components, then this force displacement line for the compressed members would be then the steep one. So like here we had the soft joint members, so it was quite shallow, but now we have stiff joint members and then it's quite steep. But equally we can see that the displacement of the screw is here and compression of the joint members is here. But if we now, in this setup, consider that we will have the same preload force here in the case number 2, like we had here in case number 1. If we now introduce here external load in a similar fashion, we put it in between these two curves, these two lines, we see that major part of the external load is now going to the decompression of the joint members. Maybe three quarters of the whole load, so maybe 75% seeing from the picture. And only this portion, maybe 25%, is adding the load of the screw. So when we put these two cases together, case number 1, case number 2, so we can compare them, we get this kind of graph. So case number 1, stiff screw, means that our external load is heavily increasing the load on the screw. When in case number 2, where we have a flexible screw, our external load is more going to the decompression of the joint members, and only small portion of it is adding extra stress to the screw. And this means that when we have this kind of tension-loaded screw joint, where we have pre-tension, it is beneficial to have a flexible screw and stiff joint parts, because most of the load is most of the external load is going to the decompression of the joint members and not to the screw itself.
Excuse me. So
Yes.
Is that the external load is like tension load?
Yes, that is the tension load. So no shear load cannot be drawn this in this way. It's the tension load. That was a good question. So it means that if we have this kind of bolt joint, this top plate would be pulled upwards and the bottom plate downwards.
And like, what is this application? Like, I didn't realize the case.
That's a good question. Could somebody maybe guess where would be the application for this kind of, I would say, approach?
I think it is joining two angle part, so two part.
I'm not sure if I got what you mean, but at least where this is used is an engine block. So if you look at these engine block screws we looked previously, they are fairly long. And by adding this length to the bolts, we increase the flexibility of this bolt. So this is fairly low in stiffness comparing to a short bolt. And that is the reason we want to use in the engine, because in the engine there's high dynamic loading. So it will need a lot of capacity from the load against tension. So therefore in the engine block screws, they usually are fairly long to make them more flexible. And the block is then very stiff. So this basic system is I would say everywhere where there's highly tensile loaded bolt joints, in machinery, in constructions, wherever. It might, but if you calculate the screw joint according to, for example, a Eurocode or some other codes, you might not see this action behind, but it is there, especially if you go to the German VDI 230, which is a good standard or code for calculation of dynamically loaded bolt joints. It is behind there, this principle. So once again, what we can interpret from these pictures. Case number 1, we had very stiff screw and very flexible joint members. It would introduce large part of the external load to the screw, additional load to the screw. Whereas in case number 2, we have flexible screw compared to very stiff joint members, and it means that a large part of the external load is then consumed by the compression of joint parts. And eventually the screw additional load is smaller than in case number 1. And what also we can see from here, if we would have, here is the line for preload. If the preload goes to 0, then it means that all of the external load is coming to the screw. None is going to the decompression of the joint members, of course, because there's no decompression. There's no compression on the joint members. You cannot decompress it. So therefore, in this tensile loaded, preloaded bolt joints, this preload is really, really crucial for the correct action of the bolt joint.
Excuse me, so it just occurs in local location, so it is not in all parts. If there comes to the zero deformation, means the other location of the part will be like high stress.
Yes, then all the external load is going to the screw only, and we cannot have a benefit from this decompression of the joint members. Like here in this case, you see that when we put the external load in this position, we have preloading level over here. In that point, we put the external load. Major part of the load is on this decompression of the joint members, so in the joint parts side. But if we would lower this preloading in a way that this basically this angle would be somewhere over here, then there's no room for the external load arrow. So basically, when we introduce external load over there, it would mean that all of it goes to the screw.
I mean that like the preload, they just come to the place that the screws is on, not all over the part, isn't it?
You mean in the joint parts where the loading is distributed, or what do you mean?
Yes, this is.
Well, of course, the load from the screw is at the location of the screw, but where the external load comes from, it could be somewhere out here. We don't know in this picture. It could be somewhere else, but nevertheless, the idea is that we have a loading in location of the screw with this tension. So of course there would be some components outside this bolt where this tension loading is introduced. Did you get what I mean?
So the joining part at the location of the screw, they experience the compression load, but not all over the part.
Yes, well, it depends. It's That's a good question, actually. So when we have the preloading force in the screw, that will act, I would say, in a sort of conical pressure distribution here. So you could imagine that we have a compression line from under the bolt head against this division line between the members, maybe in 45 degrees angle. But that's just a sort of a way to imagine it. Of course, this bolt will press these components all over when this joining surface is flat. But of course, the force far away from a bolt will be less. So the major compression is under the bolt head, between the bolt head and the nut.
Yes, I understand now. Thank you.
You're welcome. It's good to ask questions, so go ahead if you have it. So now if we have the preload too small, it would cause that our joint members may get loose and they might move to each other. And also the screw load is increased. And therefore that the screw load is increased, if we have a dynamic load situation, the screw is more vulnerable to the fatigue failure. And also the nut is loosened. Practically it means, again, that the stiffness of the screw should be far less than the stiffness of the joint members. And how can you reduce the stiffness of the screw? Because that would also mean that you reduce the diameter. Well, you can do that, meaning also reducing stiffness is the same as increasing flexibility. Same thing. You can increase the flexibility of the screw by increasing the clamping length or by reducing the bolt diameter. And usually this reduction of the bolt diameter is not good choice, because then we also increase the stresses in the screw. Of course, because our cross-section area is smaller. So therefore, the increasing the clamping length is the better option to increase the flexibility of the screw comparing to the joint members. And the clamping length means the length which is under compression under the screw. So like in here, if we have a through hole and a bolt and a nut, the clamping length would be the distance between the bolt head and the nut, including washer thicknesses. Note this, not only the joint part, also take into account the washers, because they also increase the clamping length. If we have a blind hole, then it would be the distance from the bolt head to the first loaded inner thread. So basically the component thickness which is being compressed with this kind of joint type. And if we have a stud, then it's pretty much the same. So the distance between the first loaded thread and the nut which is being used to tighten the stud. And we can of course increase the clamping length by just applying thicker plates. Then we of course increase this LK. But in some cases it would mean that we make the structure too heavy. And therefore sometimes it be used that we just add washers or length increasing collars or sleeves under the bolt head. And as a thumb rule, you could say that if you have a dynamically loaded joint, this LK clamping length should be at least 5 times the nominal diameter of the screw. So if you have a M20 screw and you have a dynamic loading, your bolt length or clamping length in the bolt should be at least 100 millimeters. But when you have really heavy dynamic loading, even that is not enough. So, for example, these cylinder head screws, as I mentioned, there could be the clamping length ratio could be like 10 or even more. So the clamping length between the pressing components 10 times the nominal diameter of the screw. That is the case like in cylinder head screws, because they are under really heavy dynamic loading. Under each stroke, they will experience a dynamic load variation. Do you have any questions about this? Because this is something which is really important for you to understand. There is a method to calculate these. So because it's a mathematical representation, we can calculate how much of the external load is coming to the screw and how much is going to the decompression of the joint members. But in this course, we don't do that. We just don't have time for it. But you should know this in your designs that in a tension-loaded, preloaded screw joint, you should have flexible screw compared to the joint members. So if you have something that you don't understand in this, please do ask.
I think everyone is clear because like in previous course we have a lot of calculation about this, so I think it is not a large problem also.
Okay, so you did, Seppo, make your calculation with the screw joint on this.
It is not exactly the screw joint, but like something like this, like acting at similar things and even more complicated.
Okay, good.
So can you explain again, I mean, what's the main purpose of this balance diagram? I mean, because we have two cases and I don't understand why, I mean, you have to compare these cases or how it works.
Yes, this the main idea here is to show you what is the difference between the case of stiff screw and flexible joint members comparing to flexible screw and stiff joint members.
So you want to find your external load?
I don't mean that you want to find it, but you will see, because the external load in this case number 1 and case number 2, they are equal. This red arrow is equal length in both cases. Yeah. But what is the difference is that in this case number 1, you can see that 80% of the external load is coming to the screw. And in case number 2, only 20% of the external load is coming to the screw.
Oh, okay.
That's the main thing.
Okay, thank you.
Okay, so, but from there we know that if we want to have, if the preloading is crucial also in this this type of tension-loaded screw joint, of course we need to somehow make sure that there is the tension preload that we want. So usually the tightening is done by torque. So we just we want to achieve certain preloading in the screw by tightening. And but when it comes to tightening torque of the screw is that when we tighten the screw, we introduce preload axial force, but also there will be also residual torque stress in the screw. And the combined stress, which means, of course, von Mises stress in the screw, has to remain below the yield limit of the material. And if we have properly designed and tightened the joint, it will keep its preloading force due to the spring effect of the screw for the whole lifetime of the component. But what is good to know about the tightening torque is that only about 10% of the tightening torque is transferred to preload force. And the remaining, most part of it, 90%, is consumed by friction in the connecting surfaces. We can slightly modify that if we add special lubricants and maybe low friction coatings, so we can increase the portion to maybe 20% of the tightening torque. For example, using molybdenum thread lubricants. But still, it's fairly low portion of the torque that we can really introduce to the preloading force of the screw. Which means that friction is quite important factor in tightening of the screw joint. And it's even more important with the stainless screws because they tend to stick quite heavily to the counterpart. And therefore, lubricants should always be used when you have stainless screws and if you want to preload them correctly. Of course, if it's not that crucial load-carrying bolt joint, it doesn't matter. But if you have a load-carrying joint and you need to achieve certain preload, you need to use lubricant with the stainless screws. And the variation in the axial preloading, the preload in the bolt of the screw, it's largely due to the friction variation between the components. And that's quite difficult to control. There is always some variation in the friction between the components, some differences in the manufacturing, some differences in the surface roughness of the washers and thread and bolts, etc. A little bit dirt, maybe some oil, etc. And that causes a variation in the friction and causes a variation in the preloading force. Now, factors that do affect to the tightening torque are, of course, bolt material, meaning the strength. If you have higher strength, you can preload them harder than the softer ones. Then this previously mentioned friction in threads, under bolt head, under nuts. Also tightening method. Compressive components in joint. If you have gaskets in the joint, that will also affect, and the previously mentioned clamping length. This tightening torque, it can be calculated with the standardized equations, or you can select it from tables. But always these tabulated values should be considered as estimates because they always include some kind of guess value for the friction, which might be the correct for your application, or then it might not. So it's more or less estimate. And if you need really precise preloading and you use torque tightening, you should do a little bit tests how you can achieve the preloading and what kind of the tightening, realized tightening torque could be. So if you have a really high safety requirements, the preloading need to be checked with methods like strain gauge, or you can use this kind of loading indicating washer, as you can see in the picture. So there's a little bit this kind of small bubbles or spots in the washer, and when you tighten these so that these bubbles just are being leveled off, so it's completely flat, then you will know that this preloading has been achieved. Or you can use special measurement washers, which has some measurement device inside the washer, and then it will tell you how much preloading force there is acting in the bolt. So in the assembly, you need to consider proper tools, proper tightening method, use suitable lubrication, and also secure the bolt joint. So usually people think that a screw joint is very simple. Yeah, in a basic form it is, but if you want to do it in a precise way, it's far from simple. It's actually quite difficult to make it very precise. And now we know that this tightening torque control is the crucial for the joint action. For that we can use a normal torque wrench, this kind of manual wrench which you can buy from a shop, and that is applicable from 0 to 500 Newton meters. Most workshop actions can be and tightenings can be done with this kind of wrench. And if you use a torque multiplier, which is basically a gear, you can get even up to 2000 Newton meters with this kind of device with a long lever arm. But if you go up from there, then you would need a hydraulic wrench. We use hydraulics to enable the tightening. The accuracy isn't that good, so it's plus minus 10% with this kind of devices. Here is a tool called Stealth, which is used for hydraulic tensioning of the bolt. But all of these, the drawback of these is that they will introduce residual torque shear into the bolt because we tighten it by turning. And if you really want to have a precise torque control of the tensile preload of the screw, you would need to use this kind of hydraulic tensioner, because this doesn't turn the bolt, it only pulls it. So there will be no residual torque shear, and you can achieve higher preload also. And if you are using really large size bolts like M100 or something like that, it is, I would say, it's the only option, because the tightening torque needed for a bolt size M100 would be huge. So you basically only options is to use this kind of tightening tool. There's a presentation about a video how this works. I think you could watch that by your own, so that we don't spend the time from your project work guidance, but it's quite interesting. The basic idea is that this tightening tool, this red component, is screwed to the top of the screw. So it's basically a nut, a special nut. Before that, the blue part has been installed, and also this special nut which is then used to tighten the whole system. And then using this red part, this screw is then tensioned. So it's adding a hydraulic force into this system. So basically this red part is working as a hydraulic piston, and it's pulling the screw slightly. And when it's pulling the screw, we can turn by hand. We can turn this component number 9, which is nut, to meet against the flat surface of the joint members. And then when we release the pressure, we can have the achieved preload in the screw joint. And this is the most precise method for introducing preload. Even the torque wrench isn't as good.
Excuse me?
Yes.
So, between the torque wrench and the washer that you presented before, which is like more popular and which is more payment fit? Because I see that is quite similar to each other.
You mean this and this one?
Yeah.
Well, from the experience what I have, torque wrench is by far more used. These are used in special applications, but of course they tend to cost money. So it is not that popular as a normal torque wrench. Torque wrench is more popular, but of course I would admit that this kind of washer is it's more precise for sure.
Yes. So the torque range is 10% or something like how much accuracy is it?
Well, how would well 10% could be something like good guess if you have a properly calibrated tool. Yeah, plus minus 10, same as a hydraulic wrench could be possible. Maybe with some special tools it could be a little bit less also.
And how about the washer? Is that 2% or something?
That I had to say it was plus minus 2%.
Yes.
So that was stated by the manufacturer of these washers. Well, how does it realize? That's another thing. But yes, it is easy to understand that this is a little bit more accurate than the torque wrench.
Yes. Thank you.
Okay, then we have a sum table for non-coated oiled steel screws with applying torque wrench in tightening. And you can find a little bit different values depending on where you look at these. But there are numerous general charts available in the internet. Then different types of standardized screws and nuts. If you use ISO or DIN screws, you can check them from this webpage. We don't go to that here. But a little bit about washers. The meaning of the washer is to reduce friction between the nut and the bolt head and between the joint components. So it will ease the tightening, and because the washer is more or less similar component always, it will also benefit that the friction might be a little bit more in control when using washers. Also, it's the intention is to reduce or prevent the damages to surfaces while tightening. We can use them as a securing method, as we looked previously, if they are specially made. And some cases they are being used to eliminate the taper surfaces effect. Like in this picture, you can see that there's a taper in this washer. These are being used, for example, against certain type of I-beams. If they are rolled, there could be some taper in the flange, and you need then this kind of washer to make the bolt act straightly. Washers can be used for sealing purposes, and they can be used to galvanically isolate components to prevent corrosion. And what is important to note that many of the washer standards, they cover only the dimensions of the washer. They specify the dimensions, but they don't specify the material. And therefore, it's important for the designer to ensure the hardness of the washer, that it will match to the strength grade of the bolt. This is really important. And if you are using 8.8 bolts, you should use 200 HV washers. But if you have a higher strength, 10.9 bolts, then you should use 300 HV washers. And the reason is that if the washer is too soft, it will plasticize. It will yield under the tightening. And then the yielding of the washer will cause that this preloading is partially lost. It will reduce the preload. And in my previous history in the company we were serving, we had an incident that there was a power line design made initially with 8.8 bolts, and at some point the calculations showed that 8.8 bolts are not enough. We need 10.9 bolts, so they were changed to the design and to the bill of materials, but the designer forgot to specify harder washers. And eventually it resulted that there were very soft washers into it. I think there were only something like 120 HV washers, which are really soft. and they did plasticize while tightening in the manufacturing, but nobody noticed it that while manufacturing. It was only noticed afterwards when these machines, they were huge wind turbine generators, they were already been delivered to the customer, and they were in offshore in the turbine. And it was a small mistake, but it caused that assembler went from Finland. It had a backpack full of washers. It flew over to England and waited for 1 or 2 weeks so that the winds would smooth down so he could go to the offshore site, because it was heavy wind time of the year. And then we lifted up to each of the turbines and manually change each of the washer in the joint to proper hardness. And it took him, I think, a couple of weeks to perform this work for all of the machines. So the cost of this operation to recover this mistake was many tens of thousands of euros. And the cost of this component is next to nothing. So keep in mind that if you have high strength bolts, you have to pay attention what is the hardness of the washer. Some guidelines for the bolt joint designs. Eurocode 3 is a general standard which is covering steel structures all over Europe. So for there is a part number 8 that covers the design of joints, but that is if you dynamic loads, in many cases you will need to and that can be applied both static and both dynamically loaded joints. And this kind of calculation we are going to perform. In Stiglitz Mechanical Engineering Design, you can also find good reading about the bolt joints, and you can also find information about this bolt joint stiffness diagram that we saw. And also there's a special book called the Big Force Handbook of Bolts and Bolted Joints. That's also more or less concentrated, focused information about the bolt joints in specific areas like pressure vessels, vehicles, aviation. So there's something to dig more into it if you are interested. Okay. For today, I don't have anything more, and as we discussed last time, we could maybe go through some of your project work topics. If you have problems, we can take separate sessions with each of you, or we can also look them together if there's something that would maybe be helpful to everyone. Have you had the possibility to start your project work? Have you progressed in that?
Well, yesterday I was watching your presentation about that, and I would like if you can repeat what's the way to start with the project, because I think it's a little bit complicated because there's a lot of parts, and I'm not sure how to start with the calculations or all of that. So if you can repeat how to start, please.
Let's see it from here. So this was your project task. So you have 2 load cases. You had to cover the blade assembly and you had to cover the operation. And the dimensions were in the picture.
I don't see the screen. I don't know why.
Okay, just a second. Can you see now?
Yes, right now.
Okay.
Thank you.
So you have two cases, blade assembly and operation, and you have to consider that this main shaft is 4 degrees backwards tilted. And the blade assembly critical point is that when these blades are being installed, 2 first blades are already brought in, and the third one is just about to be brought. So which means that these 2 blades are in this position, and it means that this blade masses will introduce bending and torque to the main shaft, because the main shaft is locked from the gearbox side. And this is something that, this is the load case you need to investigate the static strength, including notch effects. And here is the step-by-step instruction how to do it. So you have to calculate the loads. You have individual masses, and you have to calculate the loads on the shaft. So bending moment, torques, axial and shear forces, and of course including the effect of the tilt angle. You have to think about how the tilt angle affects to the bending and the torque. Then you will do the static analysis on the shaft, exactly like we did it in the exercises. You have to transfer the loads to the stresses, and also including a notch factor. And one person asked about which notch factors to use. So in this static load case, you only use the elastic notch factor, the KT. In this load case number 1, you just use the KT. The KF, the fatigue notch factor, is then being used in load case 2. And using this method, you had to define the diameters D1 and D2 and the corner radius, because that will also affect. Define the diameters that misses your safety factor against local yielding in this journal between D and D2 and this corner radius R. It is between 1.4 to 2. No more, no less. And then you will need to calculate what is realized safety factor with your selected D1 and D2 and R.
So sorry to interrupt, but the first step, the calculation of loads, we have to do the same that we did in the bending mode, all of that.
Yes.
But what it means when it says like remember effect of tilt angle, we have to put this on the formula or something?
No, it means that you have to consider what are the bending loads when your shaft is backwards 4 degrees tilted, because that will mean that it's not, these blades are not in straight, they are maybe exaggerating like this.
Yes.
And that will of course affect you. That is something which is normal mechanics. You have to consider what kind of bending loads you will have in the shaft.
Okay.
And when after doing this, I mean the diameters D1, D2, then you have the possibility to calculate the total twist, because you know the diameters, you know the lengths. Total twist in degrees for the main shaft, for the whole main shaft, meaning this length L. In that you can assume, well, I don't say anything more. You should use D1 and D separately. But when you calculate this torsional twist, we also need the torsional rigidity, which you can then calculate by dividing this torque with the total twist in degrees for the main shaft. So you have calculated certain torque with your loads, and you have the diameters. You can calculate this cross-section properties for the shaft. So you can calculate the total twist, and with that and the loading torque, you can calculate the torsional rigidity for the main shaft. And then load case 2, operation. It's dynamic load casing. So you have bending moments, which will have a mean somewhere. that is something you need to consider yourself. What is the mean value for bending moment? And there's amplitude, which is a sum of the following. So there's a sum. It's sum of mass loads from the hub, and remember 3 blades now because it's in operation. Mass of the shaft you don't need to consider, and then additionally there is amplitude bending of 150 kilonewton meters plus minus from the wind loads acting on the hub. And then there's additional torque load, which is the same for everyone. It's same for everyone for you. Its mean is 1800 kilonewton meters and the amplitude is plus minus 700 kilonewton meters. And that is acting around, of course, there's an x-axis in this figure. So it means that it's a torque to the main shaft. And the same thing basically, you just calculate the loads. These loads you need to calculate the stresses because you already calculated D1, D2. Define the von Mises for amplitude and von Mises mean stress, and then define the stresses, and then following the fatigue analysis as we did in the exercise. Okay, this was a brief presentation about how the process goes. Is there someone who would need a specific guidance with your work?
Excuse me?
Yes.
One question, like, do we limit it by the deformation or just by the stress?
You don't need to calculate the bending deflection, no. But the only deformation that you need to calculate is the twist. That is also deformation.
Yes, and do we have the limit for all that deformation?
No, there's no limit for that. You just calculate it because the main driver is that the stresses are well below the yield. So you have the safety factor which is defined, and then you just calculate what is the twist, and that's it.
And one more question, like, is that 2 bearing is like rigid, or one bearing is rigid and other is flexibility? Have flex.
The bearing system is such that it's not rigid. It's simply supported, so it allows rotation. I think I will draw it for you.
I mean that when we calculating the compression force, so if the 2 bearings is supporting against by the compression force is different from 1 bearing will support against the compression force.
Yes, that's been said here in this somewhere. I put it here. Let's see. It was here. The gearbox side bearing. So here the right-hand side bearing. That is axially locating, which means that this is carrying the axial load, which means that there is axial load in the shaft all along D1 and D2 until the bearing over here. And this front side bearing near the hub, this can move axially freely. So it doesn't carry any axial load.
And out location is that we use A and G.
Yeah, the bearing distance is A.
And when we calculated the bend, when we calculating the support for the supporting, do we use A or C?
You use A. Yeah, now I got it what you mean. You use A because this is the support distance. So you have basically this, if you consider this is a beam on the 2 supports, you have this angular supports in the bearing location, like that.
Yes, thank you.
You're welcome. Yeah, good questions. Okay. Anyone else?
Yeah.
Nikolai is saying something, but I really
Can you
can't
hear
hear
me?
you.
Sorry, what did you say?
I I just that any further questions?
Yeah, I do have a question. So, it's understand it's not really clear for me what's the difference and 3 and 4. I understand that every time we add a blade, the tension in the shaft increases, in journal increases, also the bending moment increases and the shear stress increases. But how does different positions of blades influence these stresses in our hub or in the journal? That's what unclear for me.
That is good question. It's of course from that if you have step number one, you have only mass of one blade, and you have a certain torque and certain bending from the mass of the blade, right?
Oh, so sorry for interrupting. We also take into account the torque, right?
Of course, but just keep in
Yeah.
mind that
So
you only need to cover step 3. No, you don't need to cover step 1 and step 2. But of course, you need to cover the torque, because in this, especially in this step number 3, which is the important, there's huge torque from these two blades.
from two blades, yeah, and in step 2 they are like more or less balanced, if not to say they're totally balanced. The torque come in.
Yeah, just before you are introducing the second blade, now it's here already fixed, but consider that the second blade isn't yet attached, so you have the torque from one blade like here. And now when you have just put in and fixed the second blade, that will of course balance it a bit. So therefore the most critical in the step 3 is that you have already these two blades attached and they have the torque, and the third one isn't attached, because when you attach the third blade, then it will balance itself. And the torque in the step 4 is there's no torque in the step number 4 other than coming from the wind.
So basically we need to take into account only step 3 and step 4, and we need step 3 for to calculate like the maximum shear produced by torque, and we need step 4 to calculate all normal stress.
I've made your work easier in a way that you only need to cover step 3. So you don't need to investigate what is the actual load in step 2 and step 4, and is it bigger in step 3. I already give you the information that the step 3 is the most critical one, and that is something you need to cover. But of course you wouldn't know that without calculating. So it would be hard to define that is the third blade installed and the bending causing more stress than this step 3 with two blades with a torque but without the weight of the third blade. That would need to be calculated. But I just given you the information that you can focus on the step 3.
That's great. So one final question to make it completely clear. So when we calculate shear stresses, right, so especially one produced by torque, we use the step 3 layout when the third blade is not attached, right?
Yes.
And when we calculate normal stresses, we have all 3 blades attached, and we take into account all their masses.
No.
Okay, so we only concentrate on step 3 and nothing more.
Of course, because the combination of step 3 and step 4 together would not be possible.
That's true, right? And step 3, as you already said, is the most critical. Yeah, now
Yes.
it's completely clear. Yeah, thank you a lot for this.
And about the torque, you mentioned a good point that it's really the torque in this step number 3. It's usually in the case of wind turbines, the torque induced by these two blades only. It is larger than the nominal torque of the turbine while operating. So it's really, really big torque. And in real case, they really need to do this kind of assessment for the installation for the blades regarding the strength of the shaft. Good questions. Bring it on.
Sorry, only to clarify, the difference between step 3 and 4 is that the step 3, we only have 2 blades, right? I mean, the third blade is not touching the other blade.
Yes.
Okay, so we have only to work with these 2 blades and do all the calculations about the step 3, and that's all.
That's all.
Okay, okay, thank you.
But it's not that easy. Maybe the difficulty comes when you have to think that it's tilted, because you have to think how the force vector is acting in the center of gravity of the blade when the shaft is backwards tilted. So it's not that easy to maybe not easy to find what is the correct bending and torque. But you can find it, but you need to just pay a little attention to it.
Okay, thanks.
Anything more?
Not from my side, at least.
Okay. Good. Let's continue this way, that we do this. We can follow up the project work during the next time with the discussion of a screw joint applying VDI. But I think we will have time after that also for your questions about the project work. If no other questions, then I think that we can maybe stop 2 minutes. Now, no, we don't need to stop. We can watch the video I spoke about that tensioning tool. That is something we can do here. Oh, I need to take it from the PowerPoint. Let's try to put the sounds also. Share sound. Can you see the screen?
Yes, I can.
Good. this nut is being hand tightened to meet the surface of the joint members. So now they apply the hydraulic pressure, which is then pulling the screw in tension. And of course, by doing that, compressing the joint members. And now this nut is of course slightly above the surfaces, so there's clearance, and we can tighten the, just by hand, we can tighten the nut to meet the surface again, and then release the pressure. And then take the tools away, and now we have this only this tensile preload in this screw. So there's no torque shear at all. Okay, there's nothing else for today. Jaakko has one question, so I think you are free to go. Jaakko can state your questions if you... I think it's quite okay if you share it here as well.
Yeah, it's of course it's okay. I had a problem with extracting a negative result of a function in Mathcad, relating those plots that I've been tinkering with. So I can extract the positive results quite well, but when there's like a moment plot, you have negative and positive values, and I can extract only one of those at a time. So it doesn't read, it only reads the positive value, but not the negative. So is there a trick to it? I tried minimize, but minimize doesn't, minimize does go to 0, and maximize goes to the maximum positive value. So how do I extract the negative number?
That's a good question. Now I have to say that I haven't been drawing diagrams with Mathcad, not that much, because I didn't find that so, how to say, easy to use. I've been doing that last time maybe 17 years ago, so it's slightly out of my memory at the moment, but let's see. Can you show the equation that you are using for drawing that?
Yeah, so here it is. So support A times X when X is less than D1, minus the moment when X is D1, and then support B when it's less than L, and you add the D1. I can read the maximized number here, and the position of the maximum moment, but I can't get this negative number here. So this is kind of tricky.
It is kind of tricky, so you would need to introduce there a straight line curve between those points.
Yeah, but this should do it, since this is only a minus command. This doesn't have a multiplier X. It only has the minus sign there. It should go straight down, but for some reason it doesn't. I think it might be a problem with the plotting itself, that it's, since it has no thickness, it's a straight line, so it doesn't plot it, but it has done it in previous.
Would it
previous
make difference? Would it make difference if you change the order of those functions? You would, for example, try to put this m minus x equal d1 to be the first clause or the last one. Does it affect it?
Haven't tried it. Let's try it. Oh, something.
At least something showed up.
Yeah, at least now we got something in there. No?
Now, obviously the wrong answer. Well, it's something about that array, because it seems that it draw the vertical line anyway.
Yeah, and I managed to get this, when you put a plus sign here. No, wait, was it here or here? Nope.
And maybe one option to bypass would it be if you just introduce a third equation for only the vertical line. And
Yeah.
set it to be green as well.
Yeah, for this, like substitute this, but that doesn't, like, this should be it, since this is, if I change this to a negative, it goes up from there.
Yes.
So it should, actually, why it's not showing that? It should scale this. Wait a minute. No, now it just ends there.
Yeah, but I think you by far now you found the reason why I don't use Mathcad graph functions that much. I prefer Excel for that, because I think it's much more, easy to use, at least for me.
Now I managed to mess up the whole thing. Yeah, but yeah, that vertical line is a problem. Since, but it doesn't. But does it exist? Like, really, we draw it, but does it exist in the?
It's actually arbitrary. So the bending moment in that location, it's between those values, but it's undefined.
Yeah, that's what I thought, that there actually isn't a line there. It just abruptly just disappears here and appears here.
Well, there is a line there, because there should be a line that connects the function, but it's just defined it's just between those 2 points, and it's not possible to say what is the exact value. But then on the calculation, of course, we use the absolute maximum value for it.
Yeah. But yeah, so you haven't extracted negative numbers out of a function?
No.
Before, yeah. So,
or if I did, I don't remember it anymore.
Yeah, there is the maximize and minimize function, but it only goes to the positive side, so no idea how to get the negative number. And
but maybe you could try doing a third equation just with the sentence m minus x equal to d1, and to see would it perform.
Yeah, would it perform the?
Yes, that one.
Yeah. Let's try that.
So for the others to notice it, I don't require you to draw these bending moment diagrams with Mathcad. So you can do that by hand or using Jig. You can use also Jig software if you like.
So where did you go?
Somewhere. That's curious.
Yeah, that's curious. That doesn't appear at all. Sometimes this does.
Seems like something with the plotting, like a plotting error or something.
Yeah. Of course, I don't have the functions now here. Main. Whoop. This is bad also in this. Let's try copying the whole thing to a new document. Nope. So it doesn't recognize this as a function at all. Well, of course, doesn't have anything to subtract that from.
Yeah, that's true. It just doesn't start. I don't remember if there was a possibility in MathCAD to just draw a line between 2 points, define the points, and then it would plot a line between them.
Well, now I got a line there.
Yeah.
That
Horizontal.
doesn't work. Yeah, but that doesn't work. I know that the answer is there, but it's the same thing that last time, that I know and kind of know how to do it, but still don't. Maybe if I sleep on it. But I had the same problem yesterday.
Have you
Yesterday
tried to Google draw vertical line?
Of course. I tried to, like, there's a few good videos about plotting shear moments. Shear there. There's a few good videos by this guy, Gil Lasagna engineering videos. These are quite good. Yeah, there's a lot of these. This is just one of these. The guy makes all sorts of engineering calculations on MathCAD and various other programs, but even it doesn't, like, it shows only one particular, like, situation. He doesn't go over, like, if this changes, what happens to this, and
Yeah.
for example here.
Okay, I need to move to another place in 3 minutes, so thank you for today. Hopefully, if you get that solved, send the information for everyone as well. That would be interesting to know how to draw it in MathCAD. But for others to know, I don't require you to draw these diagrams with MathCAD. So just plain manually done drawings or using Jig is quite fine.
Yeah, I'm insane. So.
But if you need any help with MathCAD, Jaakko is the guy to ask from.
Yeah, I can of course help with that, and also with SolidWorks.